So welcome back everybody for today's session of the Cardiff Analysis Seminar. Today we're delighted to have Walter Strauss from Brown University, who will talk about modulational instability of Stokes waves. So over to you.
Well, thank you. Thank you very much for the invitation. It's especially nice to see Jonathan. So I'm going to talk about a proof of a certain kind of instability of water waves. And everything in this lecture is joint work with Huy Nguyen, who's a postdoc at Brown and is about to accept a tenure track offer somewhere. Okay, so let me see. Oh, oops. Oh yeah, there we go. Okay, so it's an outline. So mostly I'm gonna talk about the background of this problem, and I'll state the main result, and then it has to be formulated appropriately. Then I'm going to prove instability, and so I'm going to prove linear instability. I'll explain that in a moment. And so we linearize the whole problem. And then the rest of basically most of what I'm talking about is an outline of the proof of the instability. So let me start by saying what the basic problem is. Okay. Whoops. Okay. A Stokes. Okay. So we talk about water waves. So maybe I should just. Whoops. Wait a moment. Yeah, like there's a nice water wave. A little picture of a water wave goes up and down, and there's a bottom. So it's the bottom, say, of the ocean, and there's some wave on top, air on top. Air is on top, and water, and there's just water. That's a little picture. I'll get back. So we're talking about water waves. The Stokes wave is a water wave that's periodic. So you saw in that picture it was periodic, and it's traveling in a fixed direction at a fixed speed in a horizontal direction. And what does instability mean? It just means that if you take a little perturbation at time 0 and you solve the equations for the water waves, then the question is, does it remain as a small perturbation for all time? That would be stable, or if it doesn't, it would be unstable. So there could be even a rather large time where it diverges from being small. It's not small anymore, and that would be unstable. So there are lots of instabilities that are very famous. The water wave theory goes back more than 200 years, and there are all kinds of instabilities, such as they're called the Rayleigh-Taylor instability, Kelvin-Helmholtz instability, and so on. Which I won't talk about. I'm talking about one particular kind of instability. So here's more specifically what kind of instability I'm talking about. So you take by a Stokes wave, I said it was a periodic traveling water wave. And now if you perturb it in a certain way, you perturb it by changing its period. So it's spatial period. So it starts out periodic, that's a Stokes wave, and then you give it you perturb it by a slightly different wave number. The wave number is the period, the spatial period. So here's sine of delta x. Well, delta is small. That's a slightly different wave number. That's the perturbation. And the whole amplitude is small. That's the epsilon. And you perturb it by that. And then the claim is that a Stokes wave will be unstable. So it will seriously deviate from the original wave. And this has two names that are commonly used. One is called modulational instability, and another word that's commonly used is the Benjamin and Feir instability, because those guys were the ones who really discovered it. Well, let's see, what am I doing here? So that's not moving. Oh, there we go. Okay. Okay, so what's the mathematical model? You just take the standard Euler equations for water waves. And there's a free boundary between the water and the air. So here's a little picture of nice parallel waves. They're pretty small, small parallel waves. And maybe it's in the Rhine, it looks like it's the Rhine River, I don't remember. And the assumption that besides the Euler equations for the water, those Euler equations, in those Euler equations, we're assuming it's incompressible. It's a 2D, it's 2D, two-dimensional. That means it's like this picture where in one horizontal direction, it's basically the same. So you just look at the cross section, like in the next picture. You look at that cross section, that's the cross section. You don't consider the other horizontal variable. So that's quite frequently studied. And it's irrotational flow and there's no viscosity. That's a so-called ideal water wave. And then you have the surface. The surface is an unknown S. And there are two conditions. One is that the pressure is constant, namely the pressure at the surface is equal to the air pressure from above. And the other is that particles on S remain on S. You don't have any things like jets or like bubbling up or something from the water. So those are the conditions. And now I'm going to write down the model. Okay, so I'm going to write down the mathematics. So omega is the fluid domain. In general, it depends on time. It changes with time. And the surface changes with time. That's the upper boundary of that. The lower boundary, there's no lower boundary. I'm assuming that it's infinite depth here. So in the, let me go back for a moment. The notation I'm using is y is vertical, x is horizontal, and the other horizontal variable I ignore entirely. And the surface is given by some graph of the vertical as a function of the horizontal in time, and has a certain period L, and there's gravity. Gravity is the main force. And the bottom, in this, I'm going to be emphasizing the case where this is at infinity depth. Okay, so y is the vertical coordinate. And because I said I'm assuming it's incompressible and irrotational, that just means, like one learns in calculus courses, that the velocity potential is a harmonic function in the water. And the velocity potential means, what that means is that its gradient of the scalar function is the velocity. Everything is a two-dimensional vector, v, because I'm neglecting the other horizontal coordinate. So we have a harmonic function inside the domain, very simple and nice. Trouble is that the surface is unknown, which means that the domain is unknown. That's the unknown we have to find. We have to find phi, and we have to find the surface. The surface is given by a function eta, like eta is the graph. The function gives you the graph. And so, okay, so you got that at the, I'm assuming infinite bottom in this lecture for simplicity. It's less algebra. So I'm assuming that it's very quiet at the infinite depth. And then the boundary conditions are these two. So this third one is just a statement that particles on the surface remain on the surface. And if you just write it down, you can see that. And the second one is the so-called Bernoulli relation, which comes from the Euler equations. I'm not writing down the original Euler equations now, but it's the Bernoulli equations, which come from the fact that the pressure in Euler equations, the pressure in the fluid on the surface is equal to the atmospheric pressure. That's the atmospheric pressure, which is a constant. And G is gravity. G is actually, gravity is quite important in this case. It's the only real force acting on, on the water. Okay. So this is the system. So it's a really simple linear PDE, but the boundary conditions are significant. And you see the boundary conditions are really nonlinear. Here it's nonlinear squared. And here it's nonlinear because it's two unknowns. Eta is unknown, that's the surface, and phi is the velocity potential. Okay. So a little bit, the history goes way back. A Stokes wave, I just repeating what I said before, Stokes wave goes back to studied by Stokes. Oh, for many years. He had a long career and he did a lot of things. And then, so I want to just emphasize that the rigorous proof of the existence of Stokes waves, of such waves, these periodic waves, didn't come until the 20th century with Nekrasov and Levi-Civita independently in the 1920s. They proved that you could make a power series expansion that had a positive radius of convergence. So they got these small Stokes waves. And now the question is, are these waves stable? So there was evidence that they might be stable, but for the kind of perturbation I'm talking about, they're not. And that was discovered basically by Benjamin and Feir in 1967. So that's about half a century ago. And that was kind of an applied math, relatively, heuristic type of argument, where you throw in a plane wave and you sort of look whether things are getting big or not. And so an actual proof didn't come until 1995, when Bridges and Mielke finally gave a rigorous proof of the instability in the case of finite depth. And they used spatial dynamics methods. They did a lot of changes of variables, and their proof does not work for infinite depth because they lose compactness. And so the purpose of my talk is to give a new proof of this, which is also a proof of infinite depth, but it's a very different proof from Bridges and Mielke. And now, just an aside, there are many approximate models of water waves. Many approximate models going back into the 19th century. The most famous one is Korteweg-de Vries equation. There are many others like nonlinear Schrodinger equation, the Whittam equation, and so on, which are models for exactly this problem, but they're approximate with some kinds of small parameters. And I'm going to skip, I won't talk about that at all. I'm going to talk about the full water wave problem without this kind of approximation. So the main result, let me see, I think I'm going to just go to the bottom of this slide here. I'm comparing this with the Bridges-Mielke proof, but the main thing is I'm going to talk about the linear instability of the problem. I'm going to take infinite depth, and the whole thing reduces, because I linearize the problem, reduces to analyzing a certain spectral problem, finding the spectrum, something about the spectrum of the linear operator, as you'll see shortly. So here's an approximate state. Well, it's a pretty accurate statement of the main result. So you take a Stokes wave. Let's say it has period 2 pi. And let's say it has, and I'm going to take small amplitude. So epsilon in this talk always means the amplitude of that Stokes wave. So it's a really small wave. And then we perturb it this way, e to the I mu x, where mu is small. So that means I'm changing, this has a very small frequency, which means a very long wave number, spatial frequency. So that's the perturbation. That's the Benjamin and Feir perturbation. And then there's going to be a linear operator, which I'll explain in a moment. And so there is the linearized operator of the equations I wrote before. And then we show that there is at least one point eigenvalue, an actual point spectrum, lambda, which looks like this. Now, see, there are two small parameters. One is the epsilon, the amplitude, and the other one is mu, which is called the Floquet parameter. It's the small frequency, spatial frequency, mu, and they're both small. And lambda has lambda depends on mu and epsilon and has this expansion. This is what we prove. That's the main theorem. That's what I'm talking about today. And notice this, yeah. So what one wants to show, I'll explain in a moment more clearly. One wants to show that there is some spectrum in the right half plane. Lambda is a complex number in the right half plane. So the real part of lambda, that means e to the lambda t grows in time. And here you have an imaginary. That's not, you can take e to that. It doesn't grow in time, but here's the real part. This is the important part. And then you have error terms. Okay, so that's the main theorem stated. Okay, now there's some numerics. It agrees with the numerics. I'll skip that. So let's formulate. Let's find this linear operator. So we have to do some play with the variable. Anyway, there are various ways to formulate this in another way. So this is one formulation of the water wave equation. It's exactly the same as what we had a moment ago. I'm just repeating it. So these are two equations on S. This is on the infinite bottom, and this is just harmonic function in the fluid. And then consider the restriction of the velocity potential to the surface. So it's just that. And that restriction, so because it's harmonic, we don't really have to talk about the harmonic function. We just can talk, if we reformulate it, about this equation on the surface and this equation on the surface. So these two equations on the surface become the two red equations. But the way I can do that is to introduce the Dirichlet-Neumann operator. So the Dirichlet-Neumann operator is the following. I have some domain. I have a harmonic function in the domain. Here's a harmonic function. Let's call it theta. Harmonic function in the domain. It has, on the surface, it has a Dirichlet boundary condition, F. And this is the not normalized normal derivative. This is the normal derivative of theta on the surface, du dn. And G, the operator G of eta, G takes the Dirichlet data to the Neumann data. That's the standard Dirichlet-Neumann operator. And then I can get rid of the harmonic function here and just write everything in terms of the surface. So we have two functions, the velocity potential on the surface, that's this guy, and the function giving the surface, and it takes this form. The first one is, these are the two equations we had up there. The first red equation is the third equation in equation 3. And this one is the Bernoulli relation, which is the second equation in equation 3. So I'm going to be dealing with this. So these equations are equations of these two quantities on the surface. And now, okay, so now let me back up just a moment and say that in the 1920s, it was proved by these two people that that Stokes wave exists for small epsilon. And in fact, Stokes, even though he didn't have a rigorous proof of convergence, had the absolutely correct expansion in terms of epsilon for small epsilon. See, the errors are all higher powers of epsilon. OC is the speed of the wave. So we're talking about a Stokes, a traveling wave of speed with speed c. So c also varies with epsilon. And okay, so we're talking just about the small. We know actually that you have a much bigger curve of traveling waves, but we're only talking about the small ones today. So I take a fixed Stokes wave. I'm going to put an asterisk on anything having to do with the fixed Stokes wave, the traveling periodic wave of period 2 pi. And I'm going to, and so you can make some, we're going to linearize. Linearization is not so straightforward because the surface is unknown. And so you have to be quite careful. I mean, the surface is hidden inside this Dirichlet Neumann operator. So you have to be careful about how you do that. So there's this nice formula of David Lan, and there's a nice observation of Serge Alignac. And so it takes this form. And then, okay, so it takes this form when I linearize. Now notice this is a linear equation when I introduce two new variables, this guy and this guy. Oh, so I linearize. So the bar here represents the linearized variable. And so now in this notation, I have V1 and V2. And notice this is a linear equation. This is a linear equation with coefficients that depend on the Stokes wave. Okay, and now I still have the surface is still unknown. The domain is unknown. So I'm going to take this domain and map it. I take the domain, which has a wiggly top, and map it onto something which is just flat on top. Okay, so that I can use a conformal map to do that, and I'm not going to go through the details of this. We use a conformal map, and then it takes this form. I do a change of variables. So instead of those V1, V2, it's now W1, W2. So and so now it takes this form. Where, okay, so the Dirichlet Neumann operator becomes the simple one when I do that change of variables, and it's just this pseudo differential operator is just absolute D. Now D is just like derivative with respect to X. Absolute D just means when you Fourier transform, you multiply by absolute of the Fourier variable. So it's pseudo because of the absolute value. It's not a regular derivative. And this coefficient, it depends on the Stokes wave. And this coefficient, here it is, same guy. And this coefficient depends on Stokes wave. And those guys actually, as a consequence of Stokes expansion himself, their P star and M star are 1 plus big O of epsilon. And the next term, which we need, is minus 2 epsilon cosine X. And then there's an error, which is epsilon squared. And the other guy has the same beginning, although the epsilon squared terms, they're not the same function. Okay. And so if you've ever seen finite depth water waves, you'll see a lot of hyperbolic tangents where h is the depth. But in this case, I'm taking the infinite depth case, which is like when h equals infinity, and that becomes this operator. Okay, so now we're going to be dealing with this. This is the linearized system after I made a transformation, but I've done it so it's now on it's a fixed domain. Okay. And now comes the really important thing. We're going to perturb it by a little guy here. We're going to change, so we take something, we're going to write this guy, the e to the I mu x, mu j of x, as a function of x. It's not 2 pi periodic, but slightly different from 2 pi periodic by putting that mu in there. It's a little different from 2 pi periodic. It's a so-called long wave perturbation. Mu is small, in other words. And you look for solutions of the time-dependent system, which are exponential in time. So e to the lambda d. Lambda is a complex number. Mu is a small real number. And we're looking for lambda. We're trying to prove that there exists a solution like this, where lambda is in the right half plane. So this exponential in time will grow. This is sort of technically, it's not so important, but it's convenient to make this a rational number, because if mu is a rational small number, then this guy up here is as a function of x, has a period, has a finite period. You can avoid that by block transform technique. So this is the only place where I talk about rational numbers, just to justify. So when I make that change of variables, notice in the previous, this system is the one I'm really dealing with, but I make the perturbation, and the perturbation time disappears because I have e to the lambda t. So there's going to be a term with a lambda in both equations. And here's the lambda. And now in the new variables, which I'm calling u1, u2, I call capital U the 2 vector. It's lambda u equals this matrix on u. And the only difference between this system and the one on the previous slide is I have mu's appearing here and here and here. Everywhere you have a derivative, there's going to be mu's coming in. Okay, so now this is the linear operator I'm talking about, and this is the linear operator. I claim that when epsilon is small and mu is small, this operator has a point spectrum in the right half plane. Okay, that's what I'm saying here in the blue sentence. Okay, so maybe it's a good place to pause. Or yeah, it's a good place to pause. Are there any questions? Anyone want to ask a question of, because here the problem is now completely set up.
Sorry, can I ask about the dx p star in the 1, 1 term of the block matrix for L mu epsilon?
Dx, oh here, this one.
Yeah, so
It's
does that mean
multiplication operator?
It's a multiplication operator. Okay.
Yeah, that's a multiplication operator. That's a multiplication operator. Oh, that's a multiplication operator. Yeah.
Thanks.
That's all it is. Yeah, that's right. So by this type of formulation, you have to deal a little bit with pseudo-differential operator here. Everything else is a regular differential operator except this guy, which has that absolute value in it. Okay. Okay, so here, okay, I'm restating the theorem. It's the same theorem I said before. Maybe I'm stating it slightly more precisely. Okay, it says that if you take epsilon small, and then if mu is even smaller, then you have this, then there exists a lambda. It was just showing there's one eigenvalue in the right half plane. That's all I'm trying to show. But okay, so the rest of my talk is about how you find that eigenvalue without giving all the computational details. Okay, so so if I take epsilon equals 0, notice, okay, here's L. When epsilon is 0, P star is 1 and M star is 1. And so, oh yeah, and here's the mu. Okay, so here it is. The mu is in there, but those coefficients are all both 1. And so you got this matrix. And now when epsilon is 0, it's a constant coefficient operator. So you can just Fourier transform. And it's a constant coefficient operator of period 2 pi, the way we set it up. And so you can just Fourier transform. You have the Fourier series of everything, and you can write down exactly what the eigenvalue, what the spectrum is. And it has four imaginary eigenvalues near the origin. Here's I. So it's I times all this stuff. There are 4 different ones. You know, the origin has some others all along the imaginary axis. They're all imaginary. And here are the 4 near the origin. Here are the 4 that are near the origin. Mu is small. Now, if mu is actually, if both epsilon and mu are 0, so now you even simplify this further, these 4 guys just shrink to be a 4-dimensional eigenspace. The null space, that generalized null space, is 4-dimensional. And when mu becomes non-zero, that splits into 4 separate imaginary eigenvalues near the origin. Mu is small. But now we have to look at what happens with the variable coefficients. So the coefficient, those variable coefficients are what gives us the instability. So, oh yeah, okay. Okay, so now I'm going to take mu equals 0, but epsilon non-zero. So let me just go back for a moment. Here's the matrix in red, and I take mu equals 0, but I take epsilon non-zero. So if you recall, P star and M star are 1 plus some cosine terms, epsilon cosine terms. Okay, yeah, okay, here we go. And it turns out that when mu is 0, you still have a 4-dimensional space. It's still 4-dimensional null space of that operator. And there are 2, this is an actual eigenvector at the origin at lambda equals 0. This one is another one. These 2 are generalized eigenvectors, as I explain here. They generalize eigenvectors in this sense that the linear operator L of U3 is U2, and linear operator of U4 is U1. And we do a normalization, and then we get, and then we're going to use these expansions. So we're going to start from these capital U guys. They're 2 vectors. And it turns out to be really important to check very carefully their parity. So the first component odd, even odd, and so on. And they have these expansions. These are consequences of the Stokes expansion. And here they are. Here they are. These are epsilon terms, and then the error terms. And I don't have U1 here because U1 is this operator 0, 1. It's just that. That's a simple eigenvector. Okay, so you have those capital U's, and we're going to use this null space, these capital U1 to U4 explicitly. So here we go. And now we want, see, that thing was when mu is 0. And now we start from this, epsilon not 0, and now we take mu not 0 also, and we do a Lyapunov-Schmidt transformation. So what Lyapunov-Schmidt means the following. We split everything into a 4-dimensional space and everything that's left over, which is infinite dimensional. And so I use capital script capital U, to mean the four-dimensional space that I just showed you a moment ago with mu equal to 0. And I guess this is called pi. Pi is the orthogonal projection onto the infinite dimensional part, this notation. And so all I did was write the equation. The equation we want to solve is this guy. And I've just split it into two parts. It's nothing to do. One of these is, this is the infinite dimensional part, and this is the finite dimensional part. Okay, four-dimensional part. And so I look for something, for a solution, which is the four-dimensional part of this form plus an infinite dimensional part. And so, so I get J equals 1. Sorry, this should be J here. J goes from 1 to 4 here. And so this is the infinite dimensional part. I have to solve it for W in terms of U. So I can solve for W in terms of U. That's what I'm going to do next. And I think I'll, yeah, okay. And then we decompose. So L, that's the linear operator we're really talking about, this one right here. And we decompose it. You see, it's linear in mu here, and it's linear in mu here, and it's almost linear in mu here. And so you can write L mu epsilon as something plus mu, and there's no big O of mu squared term. In finite depth there is, but in infinite depth it's a little simpler. And then I expand this out, and okay, I think I will skip the details. You're going to end up with we're going to end up with sort of an equation. This equation, here's the equation for W. W is the infinite dimensional part, and I can take the inverse of this operator, which I'm going to do here, the theorem says that that operator has an inverse. And then W is formally written as a Neumann series like this, M sum like this. So the point is, I'm writing the infinite dimensional part entirely in terms of the four-dimensional part. There's no other vector in here. There's only uj and lots of operators. It looks pretty awful. So I call these the sideband functions. That's Brooke Benjamin's word that he used back in 1960s. Okay, and it turns out they're, okay, so we have to look at this thing. Okay, so there's some kind of an horrible formula for a WJ in terms of the UJs, which I just showed you. And we substitute that into the four-dimensional piece of Lyapunov-Schmidt problem. So it looks like this. So WJ is some horrible thing in terms of UJs. And we want to know whether we have a non-trivial, we want to show a lambda, an appropriate complex number lambda in the right half plane, and we want a non-trivial solution of this guy, non-trivial solution. So to get a non-trivial solution, it means it's a four-dimensional, I want non-trivial alpha 1 to alpha 4, just complex numbers. And so the determinant of this guy, a certain determinant has to be equal to 0. I want a non-trivial solution. It's 4 equations and 4 unknowns. 4 equations and 4 unknowns. So so the determinant, this 4x4 determinant should be 0. And now I split it into 2 parts. The part that doesn't involve the W, which is the complicated part, and the part that does involve. So here's the part that does involve the W, which I wrote in red, and in blue is the part that does not. So it's not that complicated. What we end up with, we have a 4x4 matrix here, which we have to look at. We have to look at, basically look at the eigenvalues of A plus B. And it's just the linear operator in a product, uj, uk, and this is just a normalization. It's practically almost equal to 1, the denominator. And this is almost the identity operator, identity 4x4 matrix. And then you have this junky term, which is unpleasant. Okay, then we actually compute that determinant using the expansions, using these expansions at the bottom of this slide. We use those expansions and powers of epsilon. Okay, so when we do that, okay, here, we're there. So let's first look at the part, if we neglected the complicated so-called sideband part, then we just have this determinant, then we're looking at the eigenvalues of this 4x4 matrix. Okay, this is, I'm just repeating myself. This is what we're looking for right here. And here's the matrix A without the sideband when you do the expansions. And one has to work very, very carefully to get this expansion. Look, it's a 4x4, it's a 4x4 matrix. And we have to make sure we write all the main terms and that the error terms are really error terms. That's the important thing. Using the even and odd, the parity of various things, some of these are 0. So that's very helpful. Okay. And if you take the determinant of this guy, you take the determinant as 24 terms, right? Of some of which are 0, then the determinant, you calculate the determinant. I'm certainly not giving you the details of the calculation, and you get this. So we will consider this as an error term later on, and this is an error term, and these are all error terms. Everything in black is an error term, and here's the term that we will consider not to be an error term. You can see it up here somewhere, but I have to look again, which it's this times this. It's this 2-2 term, the 2-2 entry and the 3-3 entry, which gives you this guy. Okay. And okay, various error terms like this. But notice that we want to set this equal to 0 and look for lambda in the right half plane. But if we set this blue thing equal to 0, we get lambda equal 1/2 I mu, which is imaginary. It's not what we want. And therefore, we found, somewhat to our surprise, that we need to look at those B terms. So we look at the B terms, and let's just go to this box here. When you include all the terms, you get this blue term that I had before, which only gives you an imaginary eigenvalue with error terms here too. And the sideband terms give you a new term right here. Gives you this term. It's a pretty long calculation. I mean, it's a detailed calculation with all those things having to be calculated. You get this term here. Remember, epsilon is small and mu is small. Okay, and I'm going to show you that we can, in a moment, that we can regard all these black terms as so-called error terms. It's not so obvious that these are error terms, but okay. So the point is you get this, the blue thing and the red thing. But now you see, if you just look at the blue and the red, you're going to get something you're going to get lambda in the right half plane. I'll show you in a moment. So, okay, I'm getting near the end. Okay, so notice the following in this box here, that if we look at the pair mu and lambda together, this is cubic. and this is cubic. And this is cubic. R1 is a constant, is a complex number constant, R2 also. So this is cubic, and this is cubic. And in fact, this is cubic too. I haven't spelled out exactly what it is. This thing does not depend on mu and epsilon. And this is a really an error term. So almost all the terms are cubic. So it's, and I want to know whether there is a lambda, blah, blah, blah. So we can just do a scaling. Let's just scale. Do a little scaling. So I'm going to do this little scaling. I'm going to write lambda equal mu times gamma. Gamma is just another convenient parameter. And I want to know that gamma there's a gamma in the right half plane. And so then I can factor this out of the previous expression. You get mu cubed, and then when we don't count the mu, then it looks like this. You don't have so many it's the same thing as I wrote before, but I've just done a little bit of scaling. So now we're looking for a gamma in the right half plane. And the blue term only gives you an imaginary guy when you put this equal to 0. But look at this term here. So if we totally neglected all the black terms, you'd have gamma, and you set this equal to 0, then you'd get gamma equals 1/2 I, and then the square, and see, it would be the square root of 1/8 times an epsilon. Okay, so in order to make this really clear, I'm going to let gamma be 1/2 I plus something small. So let's call it gamma is now 1/2 I plus kappa, some parameter, times epsilon. It's the same expression as here. I'm just writing it down here. So if I do that, then you see you'll get kappa epsilon squared. You'll get an epsilon squared out of this thing. And you have an epsilon squared here, and you have epsilon squares basically everywhere else. And so I divide by epsilon squared. So then you just get kappa squared from this blue term. And you just get minus 1/8 from the other term. And then you get other term, then you get the R1, R2 term. The R1, you still have an epsilon squared left over. And here you get an epsilon left over. And then you got even more error terms here. And we want to set this equal to 0. But if we now it becomes clear, because if epsilon equals 0, clearly the root for kappa is plus or minus 1 over the square root of 8, one of which is in the right half plane. And now with the epsilon, we're just going to use the implicit function theorem. So there's going to be a root. There are going to be 2 roots very near these 2 roots. And then and then the other black terms here, you just use the implicit function theorem. So you end up, okay, so this is what I just said, basically. You get 2 roots that look like that. And then using the implicit function theorem again for one of the other error terms, you end up, this is the theorem, which I'm repeating basically the same as what I said. There are a pair of simple roots. This is 1 over the square root of 8 here. You get, I took mu and epsilon to be positive for simplicity. So here's the imaginary part. And here it is bifurcating, the eigenvalues bifurcating from this guy, which is from this guy into one eigenvalue to the right and one eigenvalue to the left with some error terms. And these really are error terms because this is mu epsilon squared, which is clearly smaller than that. And this is mu squared, which is clearly smaller than that. And so that's the proof. So anyway, I thank you for your patience. I'll just mention a couple of remarks about this proof. There are different ways to formulate the water wave problem. One could do it somewhat differently, but we use this method using the Dirichlet-Neumann operator is basically due to Zakharov and Craig and Sulem, sometimes called the Zakharov-Craig-Sulem formulation. And there are a lot of little calculations which in that 4x4 matrix, which I I spared you the details of the calculation. They're quite explicit, but there are many of them. But I think you have to do some kind of calculation like that, no matter how you prove this. And I think it's quite important. It seems to be very important that the epsilon, we choose epsilon first, and then mu, which is the change in the long wave perturbation, is going to be small relative to the epsilon. Okay, those are just some general comments. And it opens up a lot of questions about the instability of, let's say, larger Stokes wave. We've always taken epsilon small in this proof, but I'm pretty sure that if you take the larger Stokes waves, which I haven't emphasized, those are probably also unstable, but the same kind of instability, but there's no proof of that. Anyway, thank you. Thank you very much.
Thank you very much. Thanks a lot. So, any questions for the speaker?
I'll ask a couple of questions. So, about the last thing you said. So, what happens with your proof if you start taking epsilon larger and larger? So, all the statements, your epsilon was less than some epsilon naught.
Yeah, the whole proof falls apart. I mean, we can do most of the formulation. But I'm using epsilon small all the way through the game. Epsilon, yeah, I mean, this will not work. Yeah, it's complete. It needs a totally different, all these expansions, I'm expanding in powers of mu and epsilon. So, yeah. So, yeah, it's a totally different, we would have to use detailed information about the larger Stokes wave. So there are lots of larger Stokes wave. This is very famous, actually. Even Stokes himself, although maybe not what we would call in 21st century totally rigorous, talked about the large Stokes wave, and the Stokes wave can get bigger. So these are periodic waves, but the amplitudes are bigger, and they go up to a maximum amplitude. This is a very interesting question itself. It goes up to maximum amplitude, and the maximum one is the so-called wave of greatest height. So Stokes knew about the wave of greatest height, and the wave of greatest height looks like this, with an angle. This angle, the angle between my two fingers here, is 120 degrees. Stokes showed that. That was rigorously proved. You know, after the rigorous existence of these larger Stokes waves, which was in the 1978, I think. No, 80. Wait, somewhere around there. Yeah, I think in 1978. Then it was proved that Stokes was correct. But it was proved rigorously. So, but those larger ones, actually, it's quite complicated. It's a whole long story about the larger ones.
So if I try to take the epsilons for which your proof works, and I try to take the supremum over these epsilons, the epsilon that I get to, does it have any physical significance? Or
no, that's an interesting question. How big epsilon can be, in other words, that's what you're asking, right?
Yeah.
Yeah, I don't
just
know.
artifacts of the proof.
Yeah. Yeah, I don't know. I wouldn't attempt to say how big the epsilon is. We'd have to look at the error terms. We'd have to study more about the error terms in order to see how big, how big you might be able to take epsilon. I'm sure we could get some kind of a lower bound on epsilon. We proved that there exists an epsilon naught, such that if epsilon is less than epsilon naught, everything what I said was right. The question is, what we could probably get a lower bound for epsilon naught if we worked a little bit, if we were careful. But probably the instability is probably true for the large Stokes waves too. Especially the ones that are actually most exciting are the ones right near that extreme wave of greatest height. That's the wave of greatest height is written in classical hydrodynamics books. They always quote Stokes, even the old books. We now know that there are waves very close to this guy. This is an actual corner. This is a literal corner in the wave of greatest height. You have waves that are oscillating. They oscillate right near that. The waves that are not quite greatest height have infinite numbers of oscillations. It's rather subtle. Now that was a surprise when that was discovered in the second half of the 20th century, maybe 1980s or something like that.
Interesting.
So, more questions?
Sorry, can I ask a naive question? It was, I couldn't tell to what extent detailed knowledge of the Stokes wave, the actual Stokes waves was used. Was this in the expressions for the UJs? Was that the precise place where you were using the detailed knowledge?
Yeah, what we needed was, but because everything is for small epsilon, and so we needed the expansions. So basically, the only thing we use with those expansions. So the capital U, U1 to U4 have expansions, which I wrote down, and those coefficients, the coefficients which are called P star and M star, they have expansions, 1 minus 2 cosine X plus 1 minus 2 epsilon cosine X plus big O of epsilon squared. So I think once we reduce the problem to the spectrum of the linear operator, I think the only thing we're using are those expansions. We're not doing anything else. We're just using those expansions. It's not clear when you start out how far you want to push the expansions. We've computed the big O of epsilon squared terms, and we were using that. And then we realized that in the final result, we don't need quite so many higher order terms. But those are the only things we need at that point once we ended up with a linear operator.
Thanks.
Yeah.
Walter, a small remark about the Benjamin Feir, the discovery of the Benjamin Feir instability. Jim Feir was visiting Benjamin in his laboratory in Cambridge.
I was wondering about who Mr. Feir was.
Feir wanted Benjamin to suggest an experiment for him to do, and Benjamin told him to go to the National Physical Laboratory and set up Stokes waves and to study waves that weren't of infinitesimally small amplitude to get some experimental account of the medium amplitude Stokes waves. And Feir repeatedly came back to Benjamin who thought he was incompetent, saying that he couldn't set up the waves at all because they became unstable.
In the experimental.
In the experimental regime, he couldn't set them up and have a reliable, stable regime in which he could study their amplitudes and
That was
so
a
on
big
and so forth.
surprise, wasn't it?
And so Brooke went off and he eventually came down to the laboratory and he saw that this was a careful experiment and it was absolutely true that these waves were unstable. And that's where the Benjamin and Feir instability came from. So the answer to the question about the amplitudes, one should expect to see Benjamin Feir instability phenomenon at medium amplitudes, and as you said a moment ago, right up to the highest wave.
Mm-hmm.
And that's an experimental effect, not a. I mean, Benjamin told me this story himself because he was my boss when I first started out years ago.
Mm-hmm. So I'm not quite sure how much Brooke Benjamin knew about in terms of this problem, about the work of Whittam and Lighthill. I mean, Whittam and Lighthill also had some kind of analyses, you know, I would say sort of heuristic analyses at about the same time. I'm not quite sure how much Benjamin knew about that or whether it was totally independent.
Benjamin trained as an electrical engineer, and he had learned about sideband instability of circuits, and that's where he got the idea for sideband instability in hydrodynamics. And I think his was the first introduction of that particular idea to the theory.
Mm-hmm.
He did a master's degree at Yale on electrical engineering.
Yeah, I know Brooke was trained as an engineer.
Yeah. Yeah, but an electrical engineer, not a hydrodynamic engineer, an electrical engineer.
Oh, yeah.
Anyway, I've said enough.
So I remember I was reading that Whittam, because Benjamin actually refers to Whittam and so on. Whittam did some kind of analysis starting from a variational point of view back about the same time.
Yes.
I'm not quite sure. My feeling is that it was Brooke Benjamin who really discovered this thing. But somehow Whittam was in the game too.
They were all at it. This was a very competitive team.
Yeah.
In Cambridge at the same time.
Yeah, right. So if one of those first slides I had, I mentioned Whittam and Lighthill. Lighthill, of course, was a major figure. I'm not quite sure exactly what they did. I do have a feeling that calling it the Benjamin and Feir instability is quite appropriate because it was really Brooke Benjamin who discovered it. And that was apparently it was a surprise at the time.
Oh yes. But it was new at any rate. Yeah, it was new.
No one expected this. People were thinking, oh, the little small waves, they must be stable, the little guys with epsilon small.
People had worked so hard to prove stability, existence rather. They were rather shocked to discover that what they had proved was unstable.
Yeah, that's also my impression. Yes, exactly. Yeah, right. It was shocking. It's the kind of wonderful mathematics.
Yes.
That sometimes. Yeah.
Okay. So are there any practical sort of from the point of view of waves that you observe at sea and so on? Are there practical implications to such instabilities?
Well, it implies that if you got instabilities, even for the really small waves with epsilon small, then you probably have many more instabilities that you didn't realize, elsewhere. It's kind of, I would say, it doesn't have a direct, because these are really small waves. They don't do very much. It doesn't have a
Is it
direct
related?
practical I would say it has more of a philosophical impact,
Sure.
saying things tend to be unstable. Nowadays, people talk a lot about what do you call freak waves, or
I was going to ask about that. Yeah. So is it related?
yeah,
to
they're
that?
these freak waves, or they're called by
Rogue waves.
rogue wave. Yeah, they're called rogue waves, and yeah, so it's certainly yeah, that's a different story. That's an extreme kind of instability, which has not been proven for full waterways. They've only proved, I mean, there are a lot of papers about rogue waves, but they prove that, oh, you can get a so-called rogue wave, like an isolated big wave, in like NLS models, for example, and some other model, these approximate models. But rogue waves, if we understood, sorry. Rogue waves are have a practical, if you could predict rogue wave occurring out of the blue, the rogue wave is just an isolated wave which just goes and it might overturn a ship. So, and that could have a big, if you could identify when a rogue wave might happen, that would have a big impact. So I think, you know, navies are interested in the possibility of rogue waves.
Mm-hmm.
But it's not well understood at all, I think, even though there are a whole bunch of mathematical papers nowadays. Is that right, John? You agree? Oops, I'm not sure John is there anymore.
Yes, the rogue waves are, it's not really obvious what they are. They could be the consequence of the internal waves beneath the surface, which erupt onto the surface and knock ships over without warning, because you don't see them on the surface until it's too late. That's one possibility, but I think there are many others. You know, these waves that are waves on the currents and underneath the water, and they focus and jump up and knock ships over. But as you say, the shippers would like to know what the parameters are that make the risk of rogue waves high, so that they can send the ships along different lanes. That's the sort of thing that they want to do.
Yeah. It's sort of the opposite of tsunami waves. Tsunami waves go in the deep ocean. Tsunami wave, the ship won't even notice them.
Yes, that's right. Yeah.
All this structure going on in the water, but there's a slight rise or something. But when the tsunami wave goes across the ocean and hits, say, Japan, say, or somewhere, then when it hits the beach, then it becomes huge. So that's a sort of opposite phenomenon.
Well, not really, because the energy is in the wave. It has a tiny amplitude, 1 or 2 centimeters. It rolls across a huge ocean, and all of that energy focuses on the beach. And rather, the same thing happens with a rogue wave, where the energy comes from underneath the surface and focuses at a point. It kind of blows up.
And focus.
Yes, it's about focusing energy phenomena in both cases, I think.
Yeah, that's true. Yeah.
Yeah.
It is a question of focusing the energy. Exactly.
All right. So thank you very much. If there are no more questions for the speaker, then let's thank the speaker again for the very nice talk.
It's been my pleasure.